Welcome back. That's our week 7 graduate statistics in the University of Cincinnati. That's our lab guided activity number 7. And what we'll do now is get a second problem and go more directly to test hypothesis using the z-test and confirm it with the computation of the confidence interval in the same way that I expect you to do for the independent activity. So we'll do it in a more straightforward way. All right, instead of going through all of the steps one by one, we'll use the codes that you have available now and learn to modify them. All right, let's practice that. So what's the problem? A statistics student interested in sleep habits of domestic cats took a random sample of cats and monitored their sleep. According to online resources, domestic dogs sleep on average 16 hours a day. The question of the student was whether cats have different two-tailed test, sleep habits than dogs. Now use the statistical tools you just learned today to answer this question. Consider an alpha level, a cutoff level that defines what's low, what's high probability, 0.05. So let's go through the process of hypothesis test in a more direct way this time. So the hypothesis to be tested, derived from the question, is null hypothesis. The average sleep of cats equals 16, just like the habits of dogs, right? That's the null hypothesis, no different than dogs. The alternative hypothesis is that cats sleep an amount that's different from the amount that dogs sleep. So an amount that's different from 16. Right? All right, so first thing we do, we get the data. Let's read the data in. And then we will explore the data to determine the shape of the distribution. In addition, in order to determine whether we meet the assumptions to use the central limit theorem, we also need to look at sample size. So by looking at the data set here, we see that we have 143 observations. It's a very large sample size, and we can actually look at the data set here and look at the numbers, and we know that there is only one variable inside called cat sleep. Now let's go back and start exploring the data looking at the sample size. We looked at the sample size, now we need to look at the distribution. In order to plot the histogram, as you know, we need to look at the range of data. And sleep goes between 15 and about 21, right? So let's look at create bins with that range, and I modify the bins by 1 to create the distribution. And I also asked for the mean and the median to see how close together they are as a different index of whether or not the distribution is normal. So by running the code, by looking at the distribution, we see that it looks pretty symmetric. And mean and median are pretty close together, so it suggests that we have a normally distributed data. So with this, armed with this, now we can determine whether the data meet the conditions to construct the sampling distribution using the central limit theorem. And the answer is that it does. There is independence. Sorry, I cut here that I had to correct something. So it does have independence. Sample is random. We have 144 observations, which is less than 10% of the population of domestic cats, so we're good there. And sample size and skew, we're also fine. We have more than 30 observations easily, and the sample distribution is nearly normal. Thus, we can use a two-sided z-test to test the study hypothesis. So here in question 4, I'm asking you to run a two-sided z-test. So pause the video and try to locate the piece of code that we will have to adapt to run a two-sided z-test. It's in this lab earlier on. Now if you're ready for the answer, we can go back here. Let's find where I told you this is the code you should use for a two-tailed z-test. Now we're back here to question 4, and we can copy and paste the code right there. Now let's figure out what we need to change. So we're not dealing with the data set data IQ, we're dealing with the data set cat data. So let's change this piece, cat data. And the name of the variable is cat sleep. So let me just copy from somewhere here so that I don't mess up the spelling, cat sleep. And we want to compute the number of observations because we're going to need that. And we want the X bar to be the mean of cat sleep. The null hypothesis is that it is equal, the number of hours that cat sleep is equal to the number of hours dogs sleep, which is 16. The standard error will be the standard deviation of cat sleep divided by the square root of n. The rest is all the same. This is a general formula that we'll use the rest here. So we're done. 2 times the p-norm. We're good. So the question then is, how do we interpret this very, very low p-value, right? Very, very, very close to 0. The answer is that the probability of observing a z-score at least as extreme as 23.20 standard errors above or below the mean, remember that's a two-tailed test, is very, very, very low, right? Less than 0.001, definitely less than 0.05. Now, the confidence interval is a good metric to quickly support the decision. We need, however, to pick the appropriate confidence interval given the alpha level and type of test direction. Type of test, directional versus non-directional. So for non-directional tests, and an alpha level of 0.05, the confidence interval that goes with it is the 95% confidence interval. That should make sense to you because, let me try and find a good picture here to illustrate this connection. If we have 95% in the middle, the two extremes together will have 5%. Which is our rejection areas for the null hypothesis, right? It's distributed to the two sides. So the 95% confidence interval will give us what is typical, what's likely, and leave out the two extremes. So when you're doing a bidirectional test where your alpha level is 0.05, then that's the confidence interval that you want to pair it up with. So question 6 then is for you to compute the 95% confidence interval. So what you need to do is go back and find where I say, here is the code that you will need to use when you're computing confidence intervals. So let's find it. Right here. This is the code that you need to compute confidence intervals. So let's get that, all of it, and then we'll see what we need to adapt. Let's look at that. Problem 2, cat data, blah, blah, blah. Compute the 95 confidence interval. So let's do that. I'll copy here. So we need the mean, and the mean is not the mean IQ, is the mean of cat data. And then cat sleep, right? Cat sleep. And then the z critical that we want is not the 90%, right? That leaves 0.05 in each side. We want the 0.05 to be divided into two extremes because that's our two-tail test. So we want the 0.025 percentile. Again, remembering from our class, we want to divide and get the 0.025 percentile. And then we want the standard deviation again of our cat sleep. And our n is 143. This is a general formula. We can leave as is. Everything else we can leave as is. And if we click, we have our interval. So our confidence interval tells us that with 95% confidence, the amount of hours that that domestic cat sleep is between 17.8 to 18.15, you can see that 16 is not contained within the interval, right? So let's interpret. So we started with a question. Do the sleep habits of domestic cats, are they the same or different from the sleep habits of dogs, which we know is 16 hours a day? We ran a z-test and we found that the probability of observing the average that we observed in the sample, which is 17.99 hours, almost 18 hours, is very unlikely if cats in the population did sleep just 16 hours a day, right? So the probability of finding a value as extreme as the 23 unit of deviation, standard errors, deviations from the mean is very, very, very low. So we confirmed that by looking at the confidence interval, and we're 95% confident that the average sleep is between 17.8 and 18.15, which does not include the 16. So we can conclude that data provides sufficient evidence that the sleep patterns of cat is different from the sleep patterns of dogs. And here I'm putting some statistical parameters. I'm using the Z distribution with a null center, a center of 16, which represents the null hypothesis, and a standard error of 0.09, which is the one computed from the sample. And then that gave us a Z value of 23.20, and the probability of finding something as extreme as that in either direction, right? Either greater than 23 or less than negative 23 is much, much, much less than 0.0001. And we're then 95% confident that the average hours cat's sleep is between 17.82 and 18.15. Now, when we come back, this would be done. If the exercise was that, you would be done right here. Conclude. Perfect. You answered your question. It's not the same as dogs, and it is actually somewhere between 17.8 and 18.1. Done. But when we come back, I want to go through doing the same exercise if in case we had a more directional sort of question and hypothesis. All right, so then we'll conclude, and you will be fully equipped to work on your independent activity this week. All right, see you in a bit.